So we shall get going. Um, in the last decade of the Sun Empire, the fading empire's knights created a new overpowering probing technique, the invested. And this would not be rivaled for more than a decade after the empire's fall. The archaeological record is very unclear on where this magic came from and whether it was actually magic in its entirety. The Magic knights were then capable of great feats with this technology or magic. However, they were unable to stop the empire from falling to ruin. We see in the archaeological record the Taphian Schism and then post-Empyrean bee schism, known for their idolatry of bees, of course, and also the luminous Empyrean remnants, all carrying clearly Magitech influences. Today, I am very happy to show you new findings in the archaeological record based on our research, showing that indeed Magitech that we believe to be magic is actually technological in origin and can be learned in this fading age. So USDT is the wrong way. We're going to look at how a fading age scholar such as I, in the short span of a month, learned from zero to mediocrity, the secret arts of USDTs. And especially since we already heard very in depth on what these actually are in dtrace, I'll talk more on the Linux side because that's where, that's where we end up in. So let's start by tracing my outline. I am a TypeScript developer. So I am Aapo Alasuutari. That's how you pronounce the name. I know it's really hard, but that's the fun part. I'm a TypeScript developer by day. I work in automation. My day job is in an automation user interface. By night, I become a Rust developer writing a JavaScript engine of my own. I'm also a fairly avid open source contributor / albatross. So I pop up here and there. And as said, I'm writing my own JavaScript engine, or we have a group writing the Nova JavaScript engine in Rust. And if you know anything about JavaScript, it's that it's dreadful from an optimization and performance characteristic standpoint. So bad that the only real way to understand what JavaScript is doing is to profile it. So I must provide a profiler in Nova. All of my users, potential users, if there ever are any, will be entirely lost without a proper profiler. So, okay, I need USDTs. I want to have USDTs in the engine for my users, but also, of course, for myself. That being said, a month ago, I had no idea how USDTs actually work. And even worse, I'm a loyal Arch Linux user. dtrace for Linux seems to be dead. And I tried compiling Oracle's dtrace, but that seemed to be impossible in Arch Linux, at least the newest version. Trying to Google USDTs just gave me USDT headers for C and C++, but like, what about Rust? So I figured, okay, I got to learn this. I have to learn this the hard way. There's no other way. And turns out this was the wrong way. So we'll retrace my steps up this long stairway of mediocrity in the Finnish winter. You can kind of think of these as like a training montage. You should have the eye of the tiger now playing in your back, in the back of your mind. All right. So USDTs in Rust. We already heard about the USDT crate. Unfortunately, it's Linux and OS X only. It does work great on Linux as well. It just does nothing. which works great. There's another crate called Sol, which seemed quite interesting, seemed like it would work. But it relies on CFFI. So it compiles or it just relies on the C++ headers, compiles those on the C side, and then calls FFI, CFFI on those from Rust, which kind of sounds like it's going to be very inefficient. Maybe with LTO, this will work, but call C calls probe, maybe not. I also couldn't get it to work anyway. After writing this talk, I actually found a third crate. There's a probe crate. Also, it's Linux only, which is a bit unfortunate. It does exactly what USDT crate does, works with a macro and so on. But obviously, I didn't know about this a month ago. So the probe crate also exists, but it also was a bit rough on the implementation level. So after looking at the options, I figured, okay, I want USDTs to work on Linux. I'll just adapt the USDT crate for Linux. Like how hard can that be? It can't be too hard, right? I still don't know what I'm doing. Like I know what I want to do, but I don't know how. I don't even know what USDTs actually are. And at this point, I start looking around on the internet, like at a concrete level, what is a USDT? Just please tell me, what are they? Obviously, we were told about an hour ago, but so I'm going to mostly skip this part because we already heard this, but in the dtrace USDTs, I couldn't find any technical documentation in the archaeological record by Google. I really dug deep, and it's really weird that I actually didn't find any of the real documentations. Like the Open Solaris has linked today. That was the first I ever heard about that. I was like in the old Hacker News comments where B. Cantrell and B. Greg are studiously avoiding each other's eyes. And I was in Wayback Machine reading old Sun blogs and comments where people are fighting over dtrace licensing and whether or not system tab is influenced by dtrace or not. Weird places to go to, and especially weird to find no information on like how is this actually done with all that looking. But luckily we have old-sided friends. We have now dtrace.conf for future me, and we have the USDT crate code. So that's actually kind of gets me further along. Okay, USDTs, this coming from the old-sided friends episode. USDTs are embedded in the compiled executable. Still doesn't tell me what they are. Dtrace interacts with them, and producer-consumer split is important. I'm quite clear why. And then there's this particular. Let's see if I can bring up my There's this particular. Which you can't see. Okay. There's a great issue, which I will link later, on the USDT crates GitHub repo, which explains in excruciating detail very well how USDTs actually work. It's just, you don't find it on Google. Then Pacheco has a great blog, which explains this stuff in quite good detail as well. You just can't find it. Okay. But we've heard already how dtrace USDTs actually work. What about on Linux? What about with system tab USDTs, or how they call them SDTs? They lost the U there for some reason. These are used by system tab, Linux perf, eBPF nowadays. And all of them talk about these as dtrace probes or SDTs. And some people will oh yeah. I just to underline that, Joe, happy and schism, B schism. These are system tap and UF. I just wanted to use the word schism. So that's kind of where this whole thing started. So they actually very often say that they support dtrace probes. Just is that the same as like dtrace probes, or is it something different? I couldn't find a technical documentation on Google. Again, same thing happens as with dtrace probes themselves. Except there is actually fairly good documentation in the system tab wiki, but you can't find it on Google. You need to know ELF to understand the explanation. And even if you find the wiki, you can't like looking for SDT and searching for SDT in the wiki will give you 0 results. The search is somehow broken. Also, I don't know ELF, so I didn't understand the explanation when it was staring me in the face. So nobody is really explaining how USDTs actually work, except they go. So it's time to go reverse engineering into the archaeological evidence left by the Sun Empire in their fall to ruin. And now with this, we're actually starting to get up those stairs. We're really closing in on the truth. So dtrace probes, we already heard, they're made up of the clear RAX instruction. This is the is-enabled probe. And then a NOP instruction, which is the main probe that can take arguments. Well, I'm getting a question. Yeah. Okay. So where was I? I'm sorry. So there's also an ELF section for each probe. This obviously tells dtrace where the instruction, the NOP instruction and the clear-X instruction are located. So there's essentially, there's an ELF section for the is-enabled probe and an ELF section for main probe. 2 different sections, one for each probe. So in Linux, it works the same way, right? Right? No, of course it doesn't. We're in on the money. Now we see in Linux side with the steps that probes, system tap SDT probes, there's only one NOP instruction. This is the main probe. There's only one ELF section. There's also an additional extra section, only once in each executable for offset adjustments, but let's not care about that too much. What you find may be interesting here is that there is no is-enabled probe. Instead, a probe, the NOP instruction, its ELF section can have a semaphore attached to it. This is just a 16-byte unsigned integer static value in the writable part of the executable. And it's read during runtime to compare its value to 0. If the value is larger than 0, then the is enabled value is true. But that's kind of crazy when you think about it. Like dtrace today, multiple times mentioned over and over again that the disabled probe effect should be as close to 0 as possible. This does not really sound like 0 to me. We are always, every time you see your probe or every time you're coming close to the probe, you read that 16-byte unsigned integer and compare its value to 0. Maybe this is why semaphores are actually rare in Linux. I only occasionally encountered them when looking up steps did probes on the internet. So, okay, at least the ELF is same. The LSET header sections, they should be basically the same. But no, of course they're not the same. There's some like minor differences with alignment and so on, which is probably just Unix versus Linux. But most importantly, the arguments which are defined in the else section are not defined in the same way. In dtrace, it's something like this. This is not quite correct, but you can read this and understand, aha, that's a UIN32T. Yeah, that's a core store pointer. Yeah, okay. This is what the equivalent looks on Linux. That is readable if you know the GNU assembler syntax. Mostly readable. You still need to understand what the first part there is before the @ sign. But this is basically on the left side is the size and the same sign of the argument. And on the right side is how you read this value. Where do you find the value? So, and I have actually left mistakes here, but the -1 at parentheses RDX, that would mean read an read a signed byte through the pointer, which is located in RDX. You can actually add offsets to the pointer value both before and after the parentheses, so dereferencing. And I think you can also add multiple registers together to do interesting pointer arithmetic. And this is probably another reason why semaphores are fairly rare in Linux, because you can actually do a lot of the parameter mangling that you would normally need to do after the is-enabled probe for the main probe in the arguments themselves. So now we have achieved it. We are mediocre. We have mediocre understanding of USDTs and how they work in dtrace and on Linux side in the system tab world. What now? Well, what do we do with this information? Well, we use what we've learned. So I already have a PR open in the USDT crate to make it work with Linux. It works wonderfully with that code, only the tests need some shoveling. I'll get to it. dtrace for Windows made a bit of a splash. And I'm thinking maybe that wouldn't be a bridge too far after this. Only I'm not quite sure. It kind of seems like, looking at the code, they don't yet support USDTs, so maybe we'll have to wait a bit with that. Of course, my JavaScript engine already has a PR open to use USDTs for tracing. And it's been I had that moment, the first time that I could run my program and actually see what it's doing live. That was, I thought that first moment was kind of a joke. And then I got it like, whoa, this is actually this is real. This is so cool. Side note, QEMU, that's a hypervisor, right? Or emulator, not quite sure. They were actually looking for Rust tracing involves just last week. And I think USDT would be pretty excellent there. What can you do? Well, just to make sure that no one else needs to learn USDTs or dtrace the wrong way again, write about the tech, write about USDTs, write about dtrace, write about any tech you do. Maybe do some SEO to make sure that it actually comes up on Google as well. Link to other tech writers, boost others on social media and so on, so that this information stays on top and is, available for the next generation. Right.